Hello folks. Today we'll look at what it means to look at the linearization of a function. And this is a bit of a foreshadowing of probably the most important chapter that we'll study in BC Calculus, which has to do with Taylor series. But we begin by reminding you what a linearization is, which is simply using the tangent line to approximate the curve. So let's look at this. Let's suppose that f is a differentiable function, and we're going to look at the curve near x is equal to a. And what we want to look at is the equation of the tangent line at x equals a. So we know we go through the point a comma f of a, and we know that the slope is f prime of a. So the equation of the tangent line, which is the linearization, is given by f of a, or y equals f of a, plus f prime of a times x minus a. And as I've been saying, that's a big deal. That's the equation of the tangent line to the graph of f of x at the point of interest, which in this case is x is equal to a. Now, we can use L of x to approximate f of x for values of x near x equals a. Now, you should notice that the tangent line, the linearization, and the curve agree exactly at x equals a. And it's quite possible that the farther we get away from x equals a, the less that approximation works. And so let's look at an example to help understand this. Okay, so here's our simple example to give you the feeling of this. We want to use a linearization of a nice point. This is a nice point, x equals 4, to approximate the square root of 4.04. So the function that is underlying this is the square root of x, and the point that we're looking at is x is equal to 4. That's where we'll take the linearization. And so therefore, the linearization of x at x equals 4 will be f of 4 plus f prime of 4 times x minus 4. Now remember, f of x is equal to the square root of x, so that means f prime of x is 1 over 2 times the square root of x. And so when x is equal to 4, the derivative is 1/4. So therefore we can write the linearization as f of 4, which is 2, plus f prime of 4, which is 1/4, times x minus 4. And so we're looking to approximate the square root of 4.04, and it'll be approximated by L of 4.04, which will be 2 plus 1/4 times 4.04 minus 4, which is equal, finally, to 2.01. So that'll be our approximation to the square root of 4.04 by using the tangent line to approximate. Seems simple enough? So here's another example, not quite as nice. Suppose we're looking to approximate the cosine of 1.75. So our underlying function here is cos of x, and the nice point, which we'll call a, is pi over 2. And recall that f prime of x is minus sine of x. So therefore, the linearization at the nice point, which is pi over 2, will be f of pi over 2 plus f prime of pi over 2 times x minus pi over 2. Now notice that f of pi over 2 is the cos, cos of pi over 2, which is 0, and f prime of pi over 2 is minus sine of pi over 2, which is minus 1. So therefore, L of x can simply be written as 0 plus minus 1 times x minus pi over 2, which can simplify to just pi over 2 minus x. So there's our expression for the linearization of cosine of x at pi over 2. And so we're going to approximate f of 1.75, which is the cos of 1.75, with the linearization at 1.75, and that turns out to simply be pi over 2 minus 1.75. So this number is a pretty good approximation for the cosine of 1.75. Now let's continue this discussion with an introduction to what it means, what a differential is. So we begin by saying, let's let y equals f of x be a differentiable function. And then we make this definition. The differential dy equals, by definition, f prime of x times dx. And I have found it's helpful here to think about dy and dx as being really small expressions for delta y and delta x. And so that when you think of them as being really, really small, and in fact delta x approaching 0, we get the equivalent expression that dy over dx is equal to f prime of x. Sort of the difference here is that we're thinking of dy and dx as separate entities, and that's where we get the dy equals f prime of x times dx. These ideas, I think, are best seen by a picture, so I'll attempt to draw one on the next page and hopefully help you understand a little bit more about what dy and dx really represent. Okay, so hopefully this picture will be worth 1,000 words. Let me just try to describe what we've set up. We have some function y equals f of x, which is differentiable. We're interested in it at the point where x is equal to c, and so right here we have the point c f of c. And what we do is we look at the tangent line at that point c f of c. Now, we consider a little change in x, dx, so therefore this point here is c plus delta x. And in blue, the change along the tangent line corresponding to a change in x of dx is dy. The change along the curve corresponding to a change in x of dx is delta f, and that's in red. And I guess the really important thing for you to understand here is that the smaller dx is, the closer dy and delta f will be to each other. The difference between those two, which would be given by this much right here, will approach 0. So let's see if we can write this all out. One of the things we notice, let's get the colors right, is that delta f is equal to f of c plus dx minus f of c. That's pretty easy to see. Now, let's look at dy. What we know is that L of x is equal to f of c plus f prime of c times x minus c. So what do we want to show? We want to show that dy, don't want to show, but dy is equal to L of c plus dx minus L of c. And so therefore, dy is equal to, we'll skip these steps, you can fill them in. But dy turns out to be f prime of c times dx. And that's the big deal. And that's the idea of the differential, which we've already basically talked about. So we're going to approximate, let's change colors again. We're going to approximate delta f with dy, which is equal to f prime of c times dx. And the smaller the dx is, the better this approximation will be. Get it? So let's put these ideas into practice with a simple example. So here's our example. Suppose we have the radius of a circle, and it's increasing from, let's say, c equals 10 meters to 10.1 meters. So what we want to do is estimate the change in the area. Got it? Okay, so we know that from above that the actual change can be approximated by dy, which is simply the derivative at that point times dx. So here's our work. We know that a is equal to pi r squared. So a prime is equal to 2 pi r. And we also know that dx is equal to, well, remember now, we're changing from 10 to 10.1. So all that means is dx is equal to 0.1. So therefore, dy is equal to the derivative evaluated at c. Let's write that out. A prime of 10 times 0.1, which is, well, a prime of 10 is 20 pi times 0.1. So therefore dy is equal to 2 pi. And this represents an approximation for how much the area changes as the radius goes from 10 to 10.1. It shouldn't be very hard for you to do the mathematics and show that the actual change, in other words, delta f, is exactly equal to 2.01. So meters times pi. So we're actually very close with this approximation. Here we get 2 pi, here we get 2.01 pi. Okie doke. Alrighty, so for our last application of this concept of linearization, we'll talk about Newton's method to approximate the roots of a function. And similar to the ideas behind extreme values, today's graphing calculators, especially those with a CAS system, make this method be a little passé, but it's still an interesting application of how the linearization can help us. So here's what we do. We start with a differentiable function, f of x. And what we're going to do is we're going to make a reasoned guess for what the root might be. And we'll call that first guess x sub naught. And now the method, the strategy behind this is we're going to find the tangent line to f at x sub naught and find its 0. This is what we will call x sub 1. In other words, the next guess. So that's the idea. And this is an iterative process. We can keep doing this over and over and over again until we get as close to that actual root as possible. So let's just take a look at how we would get this next root. All right, so we have this differentiable function. We're trying to find its roots. We make our first guess for the root, and we simply call that x naught. And usually we get that guess by either some algebraic manipulation or even better yet by just making a rough sketch of the graph. What we want to do then is get the equation of the tangent line. And the equation of the tangent line at this point, we've been doing this a while now, is f of x sub naught plus f prime of x sub naught times x minus x sub naught. Now the deal here is x sub 1, the next guess, is the root of L of x. And to get the root, what do? We set y equal to 0. In this case, instead of y, we're talking about L of x. We set y equal to 0, and we solve for x. And you're all smart kids, so you can do this in your head. So if we set L of x equal to 0 and solve for x, what we're going to get is x is equal to minus f of x sub naught over f prime of x sub naught plus x sub naught. Now this is the 0 of the linearization. It's the next guess, and so we denote that by calling it x sub 1. And so in general, what we have is the rule for finding the next guess wherever we are. So in other words, the n plus first guess will be depending upon the previous one. That's what an iterative process is all about. So it'll be minus f of x sub n over f prime of x sub n plus x sub n. And that's the general formula that Newton's method will follow. And a lot of these things, a lot of these applications, this iterative process can simply be done on your calculator. So now we'll look at an example that illustrates how we use Newton's method. So here's our example to help show how Newton's method might work. What we want to do is find an approximation for the solution to x cubed plus 3x plus 1 equals 0. And what I've given you here is a rough sketch of what that graph looks like. And it seems that it would be reasonable to say that the first guess might simply be minus 0.3. And I want to get my next guess. So using the formula, my next guess is equal to minus f of minus 0.3 over f prime of minus 0.3 plus minus 0.3. And so if we carry out our work carefully on this, we'll see that x sub 1 can be written as minus 0.3223. And if we keep going, what we'll see is that, let's do them out. The next one is x sub 2, and that'll turn out to be minus 0.3221. And the next one will be minus 0.3221 again. So if indeed the question was find an approximation to this equation accurate to 4 decimal places, well, here we are, 4 decimal places, they agree, and the actual solution, or correct to 4 decimal places is 0 minus 0.3221. So a lot of steps were left out there, but if you follow it along on your calculator, you'll see that this is what you get. And that's how Newton's method works, and that concludes today's lecture.